In this video, we'll explore joint and conditional probability models for continuous random variables. The ideas here are analogous to those for discrete random variables, thus we'll move more quickly. Be sure to watch the related discrete video first. Recall that the simultaneous behavior of two discrete random variables x and y can be described by their joint probability mass function, or PMF, p of x, y. Further, we can interpret the joint PMF at little x and y as the probability that variable x equals little x and variable y equals little y. Further, to be valid, the joint PMF must be non-negative across all xy pairs and must sum to 1 across all pairs. Analogously, the simultaneous behavior of two continuous random variables x and y can be described by their joint probability density function, or PDF, f of x, y. Just as is true for marginal PDFs in the continuous setting, we cannot interpret the joint PDF as a probability. Rather, just the bigger the PDF f of x, y, the more plausible the corresponding pair of xy values. Further, to be valid, the joint PDF must be non-negative across all xy pairs. Further, just as a valid discrete PMF must sum to 1 across all xy pairs, a valid continuous PDF must integrate to 1 across all xy pairs. That is, the double integral of fxy dx dy equals 1. Consider an example. Let two continuous random variables x and y have the following joint PDF. f of xy equals x minus y plus 1, where x and y can both be anywhere between 0 and 1. Whereas the marginal PDF for a single variable is a 2D curve, the joint PDF is a 3D surface. In general, the higher the PDF, the more plausible the corresponding xy coordinate. In order to be a valid PDF, the volume under the surface must equal 1. To prove that this is the case, we must calculate the double integral of the PDF with respect to x and y. The first step here is to plug in the PDF and specify the limits of the integration. Here, both x and y range from 0 to 1. We can do the integral in any order, dx or dy first, we just have to keep track. One thing that helps me is to put brackets around the inner integral and start by focusing there. When taking the integral with respect to x, note that x is the variable and y is simply a constant. Thus, the integral of x minus y plus 1 with respect to x is 1/2 x squared minus yx plus x. We then evaluate this function at x equals 1 and subtract the function evaluated at x equals 0. After completing this inner integral, we're left with the integral of 1.5 minus y dy, which we can show equals 1. Double integrals are also required to calculate joint probabilities. For example, the probability that x and y are both less than or equal to 0.5 is the double integral of the PDF evaluated on this range, for x and y both from 0 to 0.5. Conceptually, this probability corresponds to the volume under the PDF on this range of x and y both being between 0 and 0.5. This procedure is similar to our integration of the PDF across the entire support, thus I won't go through the steps. The final answer is that there's a 25% chance that both x and y are less than or equal to 0.5. I encourage you to pause your video to practice this calculation. Next, just as with discrete random variables, we can obtain the marginal models of x and y from their joint model. However, the sums needed to do so in the discrete setting are replaced by integrals in the continuous setting. For example, the PDF of x is the joint PDF of x and y integrated across all y values. That is to say, the overall plausibility that x equals little x is the combined plausibility that x equals x and y equals y across all possible y values. Similarly, the PDF of y is the joint PDF of x and y integrated across all x values. That is, the overall plausibility that y equals y is the combined plausibility that y equals y and x equals x across all possible x values. Let's try it. To obtain the PDF for x, we can integrate the joint PDF f of xy across all y values. This idea is represented by the arrows in the plot. Each arrow has a fixed x value but sweeps across the PDF along the entire range of y values. The PDF of the corresponding x value of the arrow is then the density accumulated across this range. Let's do it. Plugging in the PDF and the limits of y, the PDF of x is the integral of x minus y plus 1 dy from y equals 0 to 1. Since we're integrating with respect to y, note that y is the variable and we can treat x like a constant. Thus the integral is xy minus 1/2 y squared plus y, evaluated for y from 0 to 1. We then plug in 1 for y and subtract what we get when we plug in 0 for y. We've thus shown that the marginal PDF of x is x plus 0.5 for x from 0 to 1. And importantly, this formula only depends upon x, not y. Again, because it is the marginal PDF of x alone. The marginal PDF of x plotted here at left is consistent with the patterns in the joint PDF. For example, just as the PDF of x is lowest when x equals 0, the total density across y in the joint PDF is also lowest when x equals 0. The density then increases linearly as x increases to 1. Similarly, we can prove that the PDF for y alone is 1.5 minus y for y from 0 to 1, which only depends upon y. Again, I encourage you to pause your video to confirm this result. Finally, consider conditional probability models in the continuous random variable setting. Though we cannot interpret any continuous PDFs as probabilities, we can build a continuous PDF just as we did in the discrete case. The conditional PDF of x given y equals little y equals the joint PDF of x and y divided by the marginal PDF of y alone. And this conditional PDF must satisfy the usual properties in order to be valid. Keeping in mind that x is our unknown variable here, and y equals little y is a known or assumed constant, the conditional PDF of x given y equals y can vary across different values of x, and it must be non-negative for any x value. Further, the conditional PDF must integrate to 1 across all possible values of x. Again, y is a constant here, so it doesn't make sense to integrate the PDF across y. Let's apply this result to our example. Recall the formulas for the joint PDF of x and y, and the marginal PDF of y alone. By definition, the conditional PDF of x given some outcome y equals little y equals the joint PDF divided by the marginal of y. Plugging in our formulas for these PDFs, we get x minus y plus 1 all over 1.5 minus y for x from 0 to 1. For example, if we learn that y equals 0.25, then the conditional PDF of x is obtained by plugging in y equals 0.25. After simplifying this equation, we're left with 0.8x plus 0.6 for x from 0 to 1. Again, it's important to notice here that once we plug in a specific constant y, our conditional PDF of x depends only on x. Let's think about why this conditional PDF makes sense. First, when we are given the information that y equals 0.25, we then essentially slice the joint PDF at its intersection with y equals 0.25. That is, we're essentially restricting our sample space to correspond to values where y equals 0.25. The red line in this plot represents the surface of the joint PDF at this slice. Further, this red line captures the behavior of x when y equals 0.25. In fact, when scaled, this red line represents the conditional PDF of x when y equals 0.25. Just as is true of the joint PDF when y equals 0.25, the conditional PDF notes that the plausibility of x increases linearly from 0 to 1. Again, we also see that linear increase in the joint PDF when we slice it at y equals 0.25.